Let's go on to step 5b, the second substep of step 5, which is to state the branch constitutive relations, the BCRs for the circuit. In this case, the only element type that has a noteworthy branch constitutive relation is resistors. And we say that the BCR for the resistors is called Ohm's law. The first version we're going to do of this is Ohm's law in resistance form, and that says that the voltage drop across each individual resistor is directly proportional, it's linearly related to the current running through that resistor. Another way to say that is if I look at resistor 1, the voltage drop V1, the voltage drop across resistor 1, is going to be some constant times the current running through that resistor. That constant is called resistance, and it's the stated value of that resistor. In particular, this is going to be 1 kilo ohm, which means that this individual equation actually tells me an interconnection between the variable V1 and the variable I1. Are you seeing that we're starting to make connections between those different circuit variables? We're actually saying like, hey, some of these circuit variables are directly related to the other values. Let's go on to resistor 2. We say that the current running through resistor 2 times the resistance is going to be the voltage drop across that. Another way to say that is the voltage drop across is R2 times I2. V2 equals R2 times I2. Could you guess how we get all current and voltage relationships for the entire set of resistors? That's right. Each one of these voltage drops across the individual resistors is just the resistance value of the associated resistor times the current running through. The claim of the linear algebraic nodal analysis algorithm is, hey, let's not keep this in scalar form. That's 8 separate equations that I have to track. Let's organize them in a very, very special way called matrix vector multiplication. And then let's encapsulate everything that I want to know about the relationship between voltage drops across resistors and currents running through resistors as V sub R, the voltage drops across the resistor, are going to be some matrix, a diagonal matrix with positive diagonal entries, times the currents running through the resistors in that. Now check this out. Indeed, R1 times I1 plus 0 times I2, 0 I3, all the way to the bottom. So basically, the only scalar that gets a non-zero scaling coefficient is the first one, R1 times I1. R1 times I1 is V1. In other words, I've encoded all of my Ohm's law relations for every resistor in my entire circuit as a single matrix vector multiplication. Remember that we had M sub R individual resistors. In this case, for example 2, M sub R is 8. So the number of voltage drops across the resistor, we should have 8 of those measurements. In this case, we have a diagonal matrix whose ith entry is the resistance value of the ith resistor. So if I wanted to know what the 5 element was, well, that's resistor 5, that's 1K, so that value right there should be 1,000 ohms, or if we encoded in kilo ohms, that would be equal to 1. The number of entries is going to be equal to the number of resistive elements in the circuit, so that's going to be M sub R times M sub R. In this case, it's an 8 by 8, which is exactly what we see up there. And then over here, I sub R is going to be the number of currents running through my resistors. Well, that must be the number of resistors, which is 8. So here I have an 8 by 8 times an 8 by 1 is an 8 by 1. The inner dimensions must agree. The inner dimensions cancel out, and I'm left with a vector of the outer dimensions. Here I've encoded all of Ohm's law using a matrix vector multiplication, but I know more than that. This matrix is a diagonal matrix with non-zero positive scalars on the diagonals. That immediately implies that that matrix is non-singular. So if I multiply both sides by R inverse, we note that R inverse times R, the whole idea of that is that that's the identity matrix, and then that particular set of multiplication goes away. And then over here we have this idea that now I'm going to have R inverse times V. But in electrical engineering, the inverse of resistance is called conductances. And in fact, what we've done here is we've actually restated Ohm's law in a separate way. This is called Ohm's law in conductance form. And the major idea of that statement is the current running through a resistor is directly proportional to the voltage drop across that resistor. When we look at that individual scalars of that equation, we say that the current running through is directly proportional to the voltage drop across. These proportionality contacts are just 1 divided by the corresponding resistor. So G1 is going to be 1 divided by R1. G2 is going to be 1 divided by R2. That is the exact inverse of the matrix that we expected, but we know more than that because our whole circuit laboratory experience is designed so that each of the resistors have 1K. 1 divided by 1 is 1, so this literally is going to be the identity matrix in our case. We're doing it in this development in the general case so that those of you that are super motivated, you could actually replace all the resistors with non-1K resistors and you'd still have the form of this matrix. But the concept here is now I have the currents running through the resistors as a matrix vector product of the voltage drops across the resistors, where this matrix is called the conductance matrix. G comes from electrical engineering notation. G is for conductance. We don't use C in that case because electrical engineers dedicate C for something called capacitance. That's well beyond the scope of this project. Later in my life, I hope to address that whole issue, but for now, just remember, I sub r is equal to G times V sub r is a very, very crafty way of capturing all of the Ohm's law relationships between the voltage drops across the resistors and the currents running through the resistors in conductance form. We have now finished step 5b, which was to write the branch constitutive relations, the BCRs. We're going to go on to step 5c.